Hi, my name is Wang, and I'm a master's student in physical oceanography, supervised by Eric Oliver. Today I'll be talking about the temporal and spatial variations of sea ice along the Labrador coast and shelf. So just a quick overview of the presentation. I'll first go into the background of the study region and features, and then the background of the sea ice. Then I'll talk about some of the work that I've done, and then end with some of the work that I will do. So the Labrador Coast and Shelf is a study region of great interest due to the people and wildlife that reside on the coast and depend on the sea and the ice for survival, cultural, and recreational needs. I'll start by pointing out some notable features of the Labrador Coast. So the continental shelf extends about 100 kilometers off the coast and runs parallel to the coast. The water along the shelf is relatively cold due to the cold current transported by the Labrador Current. We'll talk about this in the next slide. The Churchill River, which is the largest river on the coast, feeds into Lake Melville right here. And Lake Melville freezes over the ice season. So the Churchill River provides a large influx of water into Grosswater Bay here in spring or early summer during ice melt. We also generally see a polynya that persists each ice season in Grosswater Bay. The Labrador Current is a combination of the Baffin Island Current, the West Greenland Current, and the Hudson Bay inflow. It's the main driver of circulation off the Labrador coast. It flows south from the Arctic Ocean through Davis Strait and follows the continental shelf. It's also the main conveyor of Arctic sea ice to the east coast of North America. Since the sources are mostly from the Arctic, this water is relatively colder and less salty, so it freezes more easily. Most of the sea ice that we see on the Labrador shelf is advected from the Arctic through Baffin Bay via Davis Strait, thanks to that Labrador Current. So the images on the left here are snapshots of the sea ice over an ice season. Sea ice forms earlier in the Arctic than on the Labrador coast. We can see here that ice is being advected to the shelf in the fall, but doesn't actually reach the shelf until about December or January. Landfast ice, however, which is the ice that is fastened to the coastline, is thermodynamically or locally produced along the coast. It's also worth pointing out that the winter ice edge that we see here coincides with the thermohaline front that separates the cold, fresh Atlantic water from Baffin Bay with the warm, saltier water from the subtropical origin. The Arctic Ocean is a substantial freshwater reservoir. Large amounts of fresh water in the form of sea ice or water is exported to the Labrador coast. The figure here on the right shows the likely pathways or source regions of freshwater across the Labrador shelf and in the Labrador Current. So the dark arrows here represent water, whereas the white arrows represent ice. So you can see that most of the fresh water to the Labrador coast and shelf comes from from the Labrador Current sources that I described before. The other major sources of fresh water include continental runoff and local sea ice melting. The exported freshwater from the Arctic, along with other freshwater sources, becomes a large part of the meridional freshwater transport, making the Labrador Shelf an important region for the North Atlantic circulation. So why else is sea ice important? Sea ice is important for a number of different reasons. Firstly, it's an integral part of Inuit life in terms of both culture and living needs. It gives access to hunting and harvesting, leisure activities, and it's also an important highway for traveling between different communities and access points. So to get a sense of the scale on how the sea ice is used, this figure that's shown here by Brianna Bishop shows the main trails on the ice around Hopedale that were mapped by locals. She also indicated that the people who were mapping these trails mentioned that once everything was frozen and they were out hunting, they could be anywhere out up to this floe edge, which is marked by the black line here. Capabilities of monitoring sea ice distribution, thickness, drift, etc. are also of interest to shipping industries for marine navigation. It's also important for the survival of many different species and can affect the abundance of phytoplankton in certain regions. Sea ice variability in the Labrador coast can also have effects on deep convection and atmospheric circulation patterns, as it insulates the ocean, thus modifying air-sea buoyancy fluxes and therefore the tendency for deep convective overturning. So what kind of changes have we seen in Arctic sea ice? Well, in the past 42 years, we've observed a significant decline in Arctic sea ice extent. That's the area that the ice is covering. The IPCC reports a 12.8% decline in September sea ice. We've also seen a decrease in old ice extent. So old ice, meaning greater than 4 years old, is thicker and tends to be more resilient to changes in short-term atmospheric and oceanic changes compared to younger, thinner ice. Old ice made up 33% of Arctic ice in 1985, but in March 2020, it only made up 4.4%. There are also many reported local changes of sea ice, such as reductions in landfast ice. So changes in landfast ice are most important for local communities, as this is a type of ice that can actually be used for human activities. Some local observations include later freeze-up time, thinning ice conditions, earlier breakup time, and the increased proximity of the flow edge or the landfast ice edge. So the image here is just an example of what that landfast ice edge might look like. And then the map here on the right is a community-based map of the landfast ice edge near Pangnirtung. So the dashed lines represent the flow edge in the 1960s, whereas the solid lines represent the flow edge in present day. So we can see a large decrease in that ice extent. The data that I'm using for my research mostly comes from the Canadian Ice Services. And this data is stored in something called an egg code, shown on the left here. So Canadian Ice Services, or CIS, represents this data as polygons, like what we see on the right. So each polygon corresponds to a different egg code, which describes the ice at that location. So for example, on the right, we see the ice chart for 2 days ago, and each polygon is labeled with a letter which corresponds to an egg chart. So for example, this C polygon would correspond to the C egg chart, which gives all the descriptive information of this ice here. The different colors represent the ice type. So the pink and purple colors would be kind of like newer, thinner ice, whereas the darker greens to reds would be older, thicker ice. So we can actually see here the polynya that I was talking about earlier, which is labeled as gray ice. And gray ice is like kind of like a slush surrounded by this green labeled ice, which is thin first year ice, which is ice that is thin but developed. This data that's provided is roughly weekly since 1997. So the methods I'm using for analyzing the data can be expressed with a simple time series decomposition. Since the metrics vary in time, we can decompose each time series into their respective mean values, trends, and variabilities. So Y of t is the ice metric. So this could be ice thickness, concentration, etc. Y bar is the average value. Y trend is the long-term change. And then Y var is the variability or anomalies. So note that this can be taken over all time, seasonally, monthly, or over any defined time. So far, I've focused on the means and trends just to get a sense of the data and how it's changing. And we'll see these in the next couple of slides. So the first step of the decomposition is just getting the average values. So here I've plotted the median ice concentration and thickness grouped into 3 seasons, which I've called growing from November to January, peak, which is from February to April, and the melt, which is from May to July. So in general, we see more packed ice or higher concentrations of ice closer to the coast, and off the coast or off the shelf, the ice concentration tends to be smaller. We can also see here in the melting season that flooding caused by the influx of the Churchill River. Next, we have the seasonal trends of concentration and thickness plotted. So the negative trends in the growing season suggest a later freeze-up time. That's the blue we see here. Although it should be noted that these trends on the ice edge look really large and are a bit noisy just because there's a small sample size here. So further data processing is still needed to kind of sort that out. Overall, we see that the thickness, especially in the peak season, tends to be decreasing. So part of the goal of my thesis research is to analyze these trends and in the future variabilities for multiple different metrics. So in addition to concentration and thickness, we could look at the date of first and last ice, ice season length, edge of the landfast ice, and so on. Another avenue of my project is to use a coupled numerical ocean and sea ice model to model sea ice based on my results in the first part of my work mentioned before. It can also be used to model ocean and ice dynamics given different potential scenarios. So for example, if the temperature were to rise or if the ice were to stop being advected from the Arctic. This plot here is just an example of what the model output looks like compared to the CIS data. This is the average concentration for 2002. So one of the goals is to adjust the model parameters to more accurately represent the sea ice conditions in this region. Thank you for listening to my presentation, and I'm happy to take any questions now.